Good afternoon and welcome everybody. Welcome to the second Joint Astronomy Colloquium of this semester. It is a great honor to welcome Anna Frebel here today. Anna is a worldwide, broadly known expert on extremely metal poor stars, near-field cosmology, galactic archaeology, and so on, and she will tell us a lot about that today. Anna did her PhD at ANU in Canberra, where she graduated in 2006. She moved to the University of Texas at Austin on a McDonald Fellowship, and after that she became a Clay Fellow at Harvard, after which then in 2012 she became a permanent faculty member at MIT. In addition, Anna has won many prizes, among which is the Ludwig Biermann Award here in Germany, but also the Annie Jump Cannon Award from the AAS, and she is Lise Meitner lecturer in Göttingen and Innsbruck. And today Anna will tell us about dwarf galaxy archaeology, answering big questions with tiny galaxies. So let's give her a very warm welcome.
Yes, thank you so much for the introduction. It's good fun to be here. I already had good chats with some people, and of course some of you might have already seen my talk on Friday last week. I'm not going to talk about the same thing again, although there will be a little bit of overlap with Reticulum II, because this is a different crowd. So I thought I would give just a little repetition there. Anyway, so I want to update you on what we've been doing at MIT, and that's a whole lot of dwarf galaxy archaeology. And the early universe is most easily explored in this near-field cosmology kind of way by considering these three pieces: stellar archaeology, nuclear astrophysics, and dwarf galaxy archaeology. So this is the biggest part today, but it incorporates aspects of stellar archaeology, and I have a few more things to say about that in a moment. And we'll sprinkle in a little bit of nuclear astrophysics here and there when we talk about the origin of the elements. So what is stellar archaeology? We find old stars in the Milky Way today. We observe them with a variety of telescopes, and we study their chemical composition. And by doing so, we are basically studying the chemical composition of the birth gas clouds from which these stars formed. And it's then up to us to interpret and figure out how the elements that we observe in our stars here actually made it into this early gas. And that's the fun part of this work. And it could have been the first stars. It could have been second and later generations of stars, mostly supernovae. It could have been neutron star mergers or other exotic objects that provide all sorts of different types of elements to this gas. And so this is the big puzzle for us to figure out, again, what explains the chemical abundances that we observe in these old stars. But and I want to just add that stellar archaeology here refers to studying individual stars to learn about this early gas, and dwarf galaxy archaeology augments that concept by not just taking one or a few stars, but taking an entire dwarf galaxy, now found in the Milky Way here, to study what this galaxy looked like at early times, and to figure out what kind of physical and chemical conditions led to the emergence of such early galaxies. Specifically here, I'd like to add that for both stellar and dwarf galaxy archaeology, when we find stars with an iron abundance of less than -3, so 1,000th of the solar iron abundance, then we are in a regime where we can say that this amount of iron here is little enough that just one progenitor could have made it, could have been responsible for it. Now, of course, the lower we crank this number here, the more likely it will be that it's exactly one progenitor. But in the -3 or the sub-3 regime, we're close enough that we can say it's in all likelihood just one progenitor. And that's, of course, true for all the elements up to iron, so for supernovae. But in the case of the heavier elements, we might need to we need to broaden this a little bit and say, like, oh, maybe there was just one nucleosynthesis event. And I'll tell a little bit more about that in a little bit. So this concept highlights that the most metal poor stars are a great tool for near-field cosmology, so answering big questions with local objects, because they are right here in the Milky Way, and they are equivalent to all the studies that involve the high redshift universe. Right, so today I'm going to just focus on satellite galaxies in the Milky Way. Here is a picture of all the currently known ones, and I'm going to focus on Reticulum II, which sits down here, and then Tucana II, which is down here. Both are kind of close to the LMC in this new swath of systems that have been discovered in DES around the LMC and the SMC. I want to give some more introduction on what dwarf galaxies actually are and what their properties are. As you can see in this graph here, this is actually the average metallicity per galaxy, and this is luminosity. And you can see these are the classical dwarf spheroidal galaxies, the ones that have been known for decades and studied to death. And then much fainter, orders of magnitude fainter, are these new ones, the ultra-faint dwarf galaxies with 10 to the 3, 4, 5, 6 solar luminosities. And I did a chi by eye here with my red line to highlight what kind of strong metallicity-luminosity relationship we have here. So the fainter the system, the lower the average metallicity of the whole system. Right, and I want to specifically highlight, this is -3 here. I already mentioned -3 as sort of an important threshold where we get into the one progenitor regime. And you can see that these systems here, again, the whole system on average has something close to -3, and who knows what we're going to find here. So that highlights or underpins the concept of, again, dwarf galaxy archaeology, that we really can probe very early, very limited number of nucleosynthesis events in these dwarf galaxies, because whatever they produced in terms of the elements was so little that all the stars come out to have a metallicity below -2.5 or so. All right, so very important, and this is summarized also here. So not only are they very low in luminosity, they're also highly dark matter dominated, so they have basically a big fat dark matter halo, and just very few stars reside in the center, although I'll have to say a little bit about that towards the end of my talk. They are very metal poor, and some independent studies have shown that they are also old. So the age-old issue that for the halo stars we always claim, oh, they're very metal poor, and they're probably really old, is confirmed here, because you can make a color magnitude diagram analysis of these systems and get an independent age this way, and so we know that they are metal poor and old, and consequently they only had a few bursts of star formation. This highlights again what I just said. It's a histogram of all the stars and all the ultra faints, and most of the stars really are quite metal poor. -2.5 here is the peak, and -3 is this specific threshold. But again, this is the signature of ancient systems. So that brings me to the overview of my talk. I mostly want to talk about these three things, and if I have a little bit of time, I'll tell you a little bit about something cool at the end. We'll see. So I'll start with Reticulum II. That's an R-process galaxy that we discovered a number of years ago, and that helps us to understand the origin of the heaviest elements. And this kind of goes along with this, because we are doing a new type of chemical tagging using R-process stars to learn about the assembly, the assembly history of the Milky Way's halo. And then this is another big subject here, the most metal poor galaxy, Tucana II, that we have recently studied. It seems to have an extended halo, and so dwarf galaxies may not quite look like the way we thought they do. And as I said, maybe I have time to talk to you about asymmetric first supernovae. All right, good. So Reticulum II, small dwarf galaxy. You remember it was in the bottom of my my dwarf galaxy plot there, close to the LMC and SMC. We observed the 7 brightest stars that you can see here in this color magnitude diagram. And with the Magellan telescope, you see a little pretty movie here. And we spent several hours on each of those stars. And at the time, we wanted to just figure out, what this galaxy was like, because we had studied a whole number of others, and we just wanted to kind of take a look. And so that's what we did. We had to kind of look twice, though, because we were very surprised. Usually this is what dwarf galaxy spectra look like. When you look at the line positions here of europium and barium, you see basically nothing, maybe a little bit of barium, but certainly no europium. But then we found this star, that, and that, and that, and that, and that. And you can see there are whopping lines there. So what's going on? Well, if you plot here a halo star that is highly R-process enhanced, you see looks quite similar. Maybe we found some R-process stars in a dwarf galaxy, and we had never really found a strongly enhanced R-process star in a galaxy before. So my former student, Alex G., did the analysis of these spectra, and you can see here in black the abundances that he obtained. In purple, overlaid, is the scaled solar R-process pattern. So that's the pattern that seems to be universal. All these heavy elements, starting with barium here, and europium, follows this pattern. It's universal. We find it in the sun, we find it in old stars, we find it in the halo, we find it now in dwarf galaxies, and it's a match. The gold line here is the pattern of the S process. So both of the rapid and slow neutron capture processes create heavy elements in these particular patterns there. So when you have these stellar abundances, you can overlay them and you can do the test, and it's going to be either one or the other if you see the lines as strong as we did. And the answer is pretty clear here. Even in the case of the most crummy spectrum, where we could measure only 2 elements, it's spot on. So if we plot this in a more conventional way, barium over hydrogen, europium over hydrogen as a function of iron over hydrogen, you can see here in gray, this is the halo trend. This is sort of normal. Europium has much less data because the line is usually weak and it's difficult to measure. And then in all the colors here, you see the dwarf galaxy stars that we have observed in the other systems. Right? And so we expected at first that, our stars should be kind of like that, because that is a key signature for dwarf galaxies, that they have really low neutron capture element abundances, really low strontium and barium. And 2 stars in Reticulum actually turn out to look exactly like that. So, all good, just as we thought. Yeah? And we wanted to just say that, yes, one more system, and dwarf galaxies always have these low neutron capture abundances. But then the other 7 turned out to be up here. And these other gray dots here are the halo R-process stars that we found, and this goes along with it. Now, why am I telling you this? What are we learning from this besides, producing some new numbers? So this is where dwarf galaxy archaeology really kind of peaks in terms of its value, because we can now start playing certain games. We can ask, how rare was this kind of event that we're seeing there? Because again, the neutron capture elements that we're observing in these stars today were not produced by the objects themselves. They somehow entered the birth gas cloud, and then the little stars that we're observing, they were formed from that gas. The question is, what was the source of these R-process elements? Right? That's the big question. And we know that in many other pretty much all other dwarf galaxies, we haven't really, or ultra-faint dwarf galaxies, we haven't really seen this kind of R-process enhancement. So we can play the game and saying, like, how rare is this sort of event? And it comes out to about 1 in 10. It's not quite exact, but just run with it for now. And you can estimate in that population of about 10 or 12 galaxies, how many supernovae would you have expected to have occurred at very early times? Just given their masses and like guesstimating how massive they were back then, and then how that would translate into a number of supernovae. And so we, even if it was a neutron star merger and not a supernova, there's of course a correlation. So we can still say that, you know, whatever R-process event happened, it was 1 per few thousand supernovae going off in the system. So it's a rare event. And hopefully LIGO will help to firm this up within the next few years, and perhaps other observations as well. So we can say something about the frequency, and then can we say something about how prolific it was? And this is, again, where dwarf galaxy archaeology really wins over stellar archaeology, because if we want to answer that question, we need to understand how much mass, how much gas was available to dilute this yield into, right? And for the first time, we know what the origin of these stars is, the host system, because these stars are in their host system right now. That might sound a little bit odd to you, but think about an R-process metal-poor halo star. Do we know where that one was born? No, we don't. We know canonically that the halo, the metal-poor halo, was built from accretion events. So all these stars formed in some small dwarf galaxy far, far away. And eventually, these little systems got eaten up by the Milky Way, and the stars got incorporated into the halo. So we do not know what their origin is, which means we cannot play this game, because we cannot estimate in what sort of gas mass and what sort of environment these stars formed. But here we can. And so we can take an estimate for the maximum mass of the galaxy, 10 to the 7 solar masses. And then we can say, like, well, a reasonable minimum mass would be 10 to the 5, which is roughly the mass of a star-forming cloud, and also roughly the mass of the gas that would be swept up by an explosion that has 10 to the 51 ergs or so. So that could be a supernova, it could be a neutron star merger. They have like roughly similar energy, so anything of this type. And so this is not a precise mass number, but it gives us a reasonable range. And so this is good, because now we can take an R-process yield, and the neutron star merger gives us the best kind of yield, and you'll see in a moment why. So if we take 10 to the minus 4.5 solar masses of europium and dump that into 10 to the 6 solar masses of gas, which is kind of in the middle here, then we can calculate that the observed abundances of a next generation star should be minus 1.2. All right, so where's minus 1.2 in europium? Here is minus 1.2. And these two decks here is the mass bracket of a factor of 100, right? This is a logarithmic scale. So this bracket nicely covers the data, and when we did the same game for barium, it also nicely covers the data. Okay, this is pretty cool, because the neutron star merger yield kind of agrees with the data. Now, what about supernovae? I had to abbreviate the story a little bit, but the astrophysical side of the R-process has been debated for 60, 70 years, and the big candidates are supernovae and neutron star merger. So wherever you have a lot of neutrons going on to make these heavy elements through the rapid neutron capture process. And so other people have suggested other objects, for example, magneto-rotational jet-driven supernovae, and they have similar yields. They are probably not quite as rare as a neutron star merger, but don't have quite as high of a yield. So you see in blue a different option for a yield that would still be okay. The question is whether these types of supernovae are actually physically plausible. Time will tell, I think. But anyone can add their favorite scenario there if they like, and see if that kind of works out. But I want to take a minute to also talk about the supernovae, because we really ruled out supernovae as the main, as the canonical core collapse supernovae, as the main process source. Why is that? Well, supernova are supposed to have a yield for europium that's and heavier elements that's 1,000 times less than that of a neutron star merger, because there doesn't seem to be enough oomph, in the neutrino-driven wind that's emerging from the proto-neutron star during the supernova. But you can see from these measurements and upper limits here that we do indeed need supernovae to be there. I mean, we cannot just suddenly cut out supernovae in general from the picture of chemical evolution and star formation. So they are there. We need to deal with them. And what we see from these abundances here is that we do actually need them to produce something, but only a little. And this is exactly what we're showing there. The yield that is 3 orders of magnitude lower than this here, or whatever this might be, fits actually exactly the data that we're seeing here. You see there's some halo data here, and these upper limits, they're probably all somewhere down there. That's my hunch, at least. And so the supernova perfectly matches that. So we have, on one hand, ruled out supernovae as the site of the main R process. On the other hand, we show that, yes, supernovae are really important, and they do need to give us just as little of the neutron capture elements as it can make, and that's exactly what we're seeing in the data. So I think that's a really nice result. Good. There's one additional item I want to talk to before I wrap up this portion here, because some pundits always say, like, well, you have metal poor stars there, and they have maybe ion abundance of -3, so they must have formed really early on in the universe because their ion abundance is so low. How does this work time-wise? Because supernovae give you really fast enrichment. And this is what we've always considered, namely that you have some first stars and they give you some elements, and you dump that into the gas, and then you magically form second and later generations of stars, and then you wait for 13 billion years, and then you observe these stars happily in the Milky Way today. Right? That's sort of the classic picture. But if you want to add a neutron star merger to this, neutron star mergers take a long time. The two things need to inspiral and eventually merge and give you these neutron capture elements in a -3 star. So somehow there's a real big timing issue here. And the solution that we found by talking to a lot of people was that this cartoon picture is very nice, but it's of course way too simplistic, and even this slightly more complicated picture is probably still too simplistic, but at least one step better. So obviously, yes, some first stars will produce elements, but they of course also give you a lot of energy injection into the host system that you should start factoring in. That means gas is getting blown out, and it takes about 100 megayears for that gas to come back down, cool, clump, and make small second generation stars, right? And so we had kind of forgotten about the dynamics up in here, and as it turns out, this delay time of 100 megayears is about the time that the shorter neutron star mergers take to inspiral and merge. So we've kind of carved out a spare 100 megayears that we need dynamically in order to actually allow the formation of these stars, because they're not going to form way out here from hot gas, right? And so that kind of saves that scenario. And I'd like to see more simulations of this here, as well as more calculations for the inspiral times of neutron star mergers, so we can better pin this down and better understand how these stars actually formed. So some big questions here about the astrophysical site. Just to summarize, it's probably not core collapse supernovae that produce the elements strontium, barium, europium, and so forth, all of the bottom half of the periodic table. More likely it is a neutron star merger, but other options remain possible depending on what their yield calculations will be. And these events are very rare, at least from an observational point of view. And of course, with LIGO, we know that there is, or there are, local neutron star mergers occurring. One has been observed so far. And I think it's quite nice that we have evidence through Reticulum II now that it was also neutron star mergers in the early universe and not some other source, because why would we have two different sources at early times and in the local universe? Now, is Reticulum the only R-processed galaxy? So I'm coming back to the 1 in 10 frequency. The jury is actually still out on that. Tucana III has been found to contain mildly R-processed enriched stars, so possibly a larger system where the yield just got diluted a little bit more. However, there are more and more voices now coming up that say that Tucana III is actually not a dwarf galaxy, it's a cluster. So it could be 2 out of 14, or it could be 1 out of 14. Again, the average is about 1 in 10. That's why I'm keeping that number there. But the point to take away here is that this R-process enhancement starts to become ubiquitous. We've seen it in ultra-faint dwarf galaxies. We've seen it in clusters. Other dwarf spheroidal galaxies have sort of also shown R-process enrichment, although it's much more murky and messy because these stars have higher metallicities where the signature isn't so clean and clear anymore. Only when you're close to the -3 in iron regime, you're in this one progenitor regime, and so you can see the signature really, really booming. And then, of course, in the halo, we have several dozen stars with strong R-process enhancement identified, and with our new effort called the R-process Alliance, we have recently almost doubled those numbers. But one question that emerges from this whole game is, can we use R-processed stars as tracers of the hierarchical merging, since they are found in all these different types of systems? Right? I already said that the halo has assembled from small dwarf galaxies, and now we seem to have this tag, this R-process enhancement, that sometimes occurs and sometimes it doesn't. But we need to understand, where the R-processed stars in the halo are coming from. And not just, from some dwarf galaxy, but no, can we quantify that? What can we learn? Because we are presented with a new tool. And we've explored this already a year and a half ago with one of my grad students, Kaylee Brower. And so we started to think more about a new type of chemical tagging. It's not the old way of how chemical tagging was kind of invented by Freeman and Blend Hawthorne in 2002, where they were saying, let's say alpha elements of halo stars should be just slightly different, and that would reflect slight differences in their individual birth environments. And if your chemical abundance measurements are just good enough, you can figure out the differences, and that tells you, these 3 stars came from such a system, and these 5 stars came from that kind of system over there. But it's just a little bit too hard to be a mainstream success. And so we are trying to think of chemical tagging now by using R-processed stars, because it's more of a binary thing. Either you have a signature or you don't, right? And we can start playing with frequencies and matching things up. So what have we done? We have here, the calculation is still with 2 out of 14 because this is a year old. We have a certain fraction of R-processed dwarf galaxies. And in the halo, we know that about 5% of metal poor stars are R-process enriched. So how many Reticulum II type systems, at this fraction here, does it take to build up the population of R-process stars in the halo? Right? That's the basic question here. And here is the answer. So we used our dark matter only n-body caterpillar simulation. That's a suite of about 30 halos that model the whole formation history of Milky Way mass galaxies. So we have a little variety in those 30 halos, not just one, because actually creating a simulation that equals that of the Milky Way is rather hard. If you have questions about that, you can ask me separately. So it gave us some statistics here, and again, we asked the question, what fraction do we need of these early systems to account for the halo R process population? And to cut to the chase, of those 5% or so, here's what you can, here's what the models can reproduce. So about half of the 5% can be provided by systems that are 10 to the 9 and 2 times 10 to the 9 solar masses. So this translates into several hundred systems that came and brought our process stars to the Milky Way. You can see that, so this is sort of the mean values here of these systems, of these types of systems. But you can see the bars here give the full range of possibilities across these 30 halos, and they very well reach into this observed range here that we have set up to 4%. The observed fraction is sort of 3, 4, 5%. There's an error bar there as well. But so we think that at least 50% of all the R-process halo stars originated in Reticulum II dwarf galaxies. So that's the upshot here. Actually, my hunch is that it's probably close to 100% because of if we don't count Tucana and if we tweak a few other things, we get up to 80%. And so I think there's a good chance that at least, at least common sense tells you that these stars need to come from somewhere, and so probably from Reticulum II type systems. Yeah, so this is half of the observed fraction here. Very good. All right, so I'd like to talk about Tucana. That's a different dwarf galaxy. And again, I give a little bit of an introduction to the problem so that you can appreciate our solution. Let's talk a little bit more about how we observe dwarf galaxies and what the challenges are. It's quite obvious that ultra-faint dwarf galaxies are faint. As you can see in this color magnitude diagram, the upper part of the giant branch here starts at 19th magnitude. So if you are interested in high-resolution spectroscopy, you're going to run out of glass really soon. 19th magnitude is about the limit for high-resolution spectroscopy. So if you want to explore the system, you're out of luck. Another issue is that, even if you have member stars identified, that doesn't come for free either. So you need to actually put in hard work to identify members. And photometric techniques until so far were also somewhat inefficient. As you can see, here is just a picture into, it's the set of coordinates in the direction of Tucana, and obviously the stars closer in have a higher membership probability, the stars further out have a lower probability, and then the cut is kind of made here around the isochrone. And again, the inner part here, the red ones, they're most likely members if they're sitting here around the turnoff, and they do cluster here towards the center. And then the further you go away from the isochrone, the less your membership probability is. And so you kind of hope that it just kind of magically works. But it's the foreground contamination is a very big issue. So to summarize that, this is what can be accessed with high-resolution spectroscopy. If you have multi-object spectroscopy and use medium resolution, you can do better. You can go down to 21st magnitude. But you can see in this dwarf galaxy, it's like halfway down the giant branch only, right? So, this is nothing, because you can also see the star density goes like way down the further you go up. The bulk of the star sits down here. So how do we get down here? Well, you have to use some kind of photometry and characterize your stars photometrically, but photometry, at least in the classical sense, doesn't give you much metallicity information, and this is what we want, right? We want to chemically study these systems, so what do we do? The solution is narrowband photometry, and with narrowband, I'll show in the next slide, but it's something centered of the calcium K line, so we get metallicity sensitivity. And that has helped, and so we've done that, and that has helped greatly to identify previously missed members, and also to figure out new spatial and chemical features, as I will show you. So we have been using the SkyMapper telescope. It's a 1.3 meter telescope in Australia. It has a huge field of view, 2 degrees squared. And we've had for years an auxiliary program with them where there was time available besides the main survey that's being carried out. And so we imaged several dwarf galaxies down to 22nd magnitude in a total of like 13 hours or so. And we've done this especially here with this V filter that you see here. It's a very narrow V filter that sent us over the calcium H and K lines, and you can see here two synthetic spectra for two different metallicities, and you can clearly see that if this is your filter width, you're going to get a lot more flux in the metal pore star because there's less absorption. So in these kinds of filters, they're ideally made for studying metal pore stars because metal pore stars just blink, right? They give you more flux. You would kind of intuitively think, oh, they give you less flux because they're more metal pore. No, because they have less absorption, they give you more light in that filter, and so they will come out on top. They kind of flow to the top in the right type of diagram. And this is exactly what we've been doing. And in order to tackle this, we've not just taken V filter data, but also U and G. And with the U filter, as you can see here, we get some gravity information. So here's color code is gravity, so the giants sit down here, and the main sequence turn of stars sit here. And you can see the giants nicely splay out. So, and we're interested in giants, right? Because that's what we primarily can access in a dwarf galaxy. So we can get foreground, we can weed out foreground stars by having gravity information for all stars in a large field around the galaxy. So that's been very, very helpful. And then here we have this magic metallicity plot, and it's color-coded with metallicity, and you see, as I said, the low metallicity stars float to the top. They don't fan out too well up here, but it's good enough to figure out candidates below -3 or below -2.5. Again, this kind of threshold value that we're interested in, right? So whatever sits up here on top is the cream, and those are the stars that we're most interested in. Now, besides that, we already have one important prior, because we know from all our previous dwarf galaxy work that these are metal pore systems. So we can actually cut out all the high metallicity stuff, assuming that it'll be foreground. Everything above -1. -1 is here, light green. So everything that's down here, we can be pretty sure it's not going to be part of an ultra-faint dwarf galaxy, because that's not what these systems are made of. So we can cut a whole bunch of foreground that way, and whatever else there floats around, because the halo metallicity on average is maybe 1.6 or maybe 1.2 if you're in the outer halo. So there is this intermediate range that needs to be cleaned from foreground contamination, and we'll do that here with the gravity portion. Okay? So that's working really well. And even before we had all of this foreground contamination figured out, we went to the telescope and with some preliminary, just here, some cream stars, so to say. And we found 2 new members in Tucana that sit quite far out and look at these metallicities. We couldn't discriminate the metallicity that well. So this is simply a sign of the metal pore nature of the system, that any random one member you pick, they're going to have a metallicity like -2.5, -3, right? Because that's what these systems are like. So we found these two, and we were like quite surprised because they're outside of the half-light radii. But then we went back to the telescope and did some more observations. In the meantime, we improved our precision of the photometry, and we have a sigma of 0.16 dex at -2 and 0.35 dex at -3.5, and that's roughly the same precision that medium resolution follow-up spectroscopy usually yields. All right, so same sort of ballpark. So we're quite happy with this, and we also worked more on the gravity precision here that you can see is like 0.2 dex or so, to again do as good as possible, because we want to get a meaningful chemical characterization, which means a meaningful metallicity distribution function. And it's going to get skewed if we don't have the precision, and it gets skewed if we have wrong stars in it, right? And the wrong stars will probably be on the metal-rich end. So if we want to get the spread of the system, we got to kind of make sure that we just don't have any junk in there if we can help it. So we also applied Gaia proper motion cuts. That helped us to weed out foregrounds, as well as here's gravity. Again, this is the galaxy, and this is the foreground junk here at high metallicity that we're cutting. These were members identified by other folks that we are now saying shouldn't be members. Then we did one more thing. Namely, again, we have this big field of view. So the question is, does Tucana look like this when we include a spatial likelihood term in our membership probability machinery? And that has always been done to date, because people think like it's a little galaxy, so it'll help it in the absence of any gravity information, and of course before Gaia, you know, a spatial likelihood term just increased your chance of fishing out all the members. But what happens if you loosen that criterion? And then it looks like this, right? These are just possible members. The red ones are the confirmed ones. And so we could play this game again because we had this huge field of view. And as it turns out, it's probably going to look like this. So we should maybe not have introduced a spatial bias when selecting members. So just to highlight this, this was all that was known in Tucana before we sank our teeth into it. And this is what it looks now. This is quite different. These are 8 half-light radii. This is quite significant. And actually, I'm going to cut to the chase right away here. This is 1 kiloparsec distance. So we found a whole bunch of members, and they're all spectroscopically confirmed. They all have... this got cut off. These are all, the blue is around -3. These are all extremely metal poor stars that we found far, far away from the galaxy. What does it mean? Well, Tucana has an extended metal poor halo, as it looks like. There could be a slight metallicity gradient. There are few more stars here. You see the small ones. We forgot to add them here, but so there are more known members here, and they're just a little bit more metal-rich than these tails here, but I'm not sure that it's truly statistically significant. What we do know is that while this looks like a spiral galaxy, it definitely is nothing like that, and it's not a tidal feature. We had someone model the system, including the effects of the LMC and the SMC, and any tidal feature should basically go like this, kind of 90 degrees compared to this. So it's not a tidal feature. What else gives you a spatially extended system? Well, in the Milky Way and in any other galaxy, you would say like, oh, if you have something that's big and puffy, it's a sign of accretion, sign of some merger. So maybe Tucana is the product of one of the earliest major mergers, namely 2 identical small galaxies that came together as part of the hierarchical merging paradigm of galaxy formation. And we just happen to see the leftover signatures of that today. At the side note, by finding stars out to 8 half-light radii, we have also providing the best mapping of stars of the extended dark matter halo. So the models for how the profile for how you model the dark matter halo with the stars can now be much better constrained, and we're currently working with some folks on that, and we have already increased the mass by a factor of 2, but it will just help to really pin down the profiles some more. Now, to wrap this up, I think extended halos are not uncommon, because if you go through the literature, you see that for Segway 1, one star has been reported to be at 4 half-light radii, when the data covered about 6 half-light radii. And for Buddhist 1, one star was also reported to be at 4 half-light radii, and the data covered about 9 half-light radii. And then Leo 4, this is just these are spectroscopic results, this is just photometry, but there are few stars where they can't quite decide whether they like this or not, but there are sort of candidates at larger than 5 and even larger than 10 half-light radii out there. And so their data gave that away. And so it's just these are only individual stars, and so people didn't know what they were looking for, and they didn't have the data that extended that far to really find a population. They just found an example, possibly. So we're going to try to re-observe these systems to see, what's up there. And considering that we only have about 15 or so of these systems, 4 or so show possibly extended stellar population is quite significant, I would say. And we haven't even looked at the rest yet, right? So we don't know. And on top of that, there are predictions that systems like that at early times had something like 10 to the 8 or 10 to the 9 solar masses, and just theoretically they should be the product of about 1 to 4 progenitor systems, which is exactly what I just told you, surmising on interpreting the observations that we saw, that this looks like a merger signature. And so theoretically a system like that, an ancient system like that, should have been assembled from a very small number of progenitors. So I think the fog is lifting a little bit, and more data will certainly help to play this game a few more times to see if we're onto something. And of course, to finish this now, here is the metallicity distribution function that we obtained for Tucana. This is smoothed a little bit, but it covers about 2 decks. We have this extra peak here, and it took us a while to figure this out, but the inherent nature of this narrowband V filter is such that a carbon band is included, and that gives extra absorption, so things look kind of a little bit distorted. And to cut a long story short, we have some good indications from some tests that these are the carbon-enhanced metal pore stars that should be in here, but in the filter they will show up there. And again, this is a side note, in the halo, a lot of the most metal pore stars are very carbon-rich, so they also need to come from somewhere, same as the R-process stars and any other stars. And so I think this is the solution to also solidifying on the origin of the carbon-rich stars in these small systems. So this is not a problem. I think this is something really cool and hidden. We just need to work a little bit harder to retranslate it back into this box here, into this bin. And you can see here that the peak here of Tucana is at -3. So we think that this is the best or the most well-established metal pore galaxy overall. How much more time do I have? -1? All right, good. I only need like 1 more minute. So we've also played the same game for Sagittarius with our selection machinery. Again, here are the metal pore stars, and we've confirmed 3 stars to be at -2.5. And we've also looked at the Sagittarius dwarf spheroidal galaxy. So the other one's ultra faint. This one is a big one, a really, really big one. And a whole bunch of metal pore stars suddenly are popping up to have -3, showing that even Sagittarius, that's the one with the Sagittarius stream, has an extended population, or a significant population of very metal pore and possibly also extremely metal pore stars. So this technique is really working well, and this is all actually just based on public data. Great. So I'm gonna cut this story here, and I want to say just a little advertisement in case you haven't heard about it. It's already been published, but in SkyMapper, the original SkyMapper survey, we found a star with minus 6.2, which is the star with the lowest measured iron abundance. There was another one discovered that had an upper limit of minus 7, but that's just an upper limit, so this is the lowest measured iron abundance. I just wanted to throw that out, and of course it is carbon rich, as you can see here. So that brings me to my summary, and I'm happy to just leave that up there and take questions.
Thank you very much, Anna, for a fascinating talk. I am sure there are many questions, and hereby I open the floor. And while people are thinking of their questions, I'm going to ask the first one. I actually have multiple, so I'll ask one first while people are thinking. So you showed halfway through your talk this comparison to the caterpillar simulations, which are dark matter only. Now, in that area, of course, people are concerned that enrichment really depends on baryonic physics. And I imagine, especially in like low binding energy systems, that would be really important. Have you thought about like looking at simulations including baryonic physics? I suppose illustrious that your neighbor Mark is doing is not quite suitable resolution-wise, but maybe fire.
We haven't really done it yet. The issue is that if you have the baryonic simulations, usually only just one. Right, so you have no variation, and we really wanted to explore variation because it's a very stochastic process, and we don't really have a good grasp for how it went. Even if Mark's simulation perfectly reproduces the Milky Way, the early history could have been totally different, and you would still get to a similar result. But in this case, I think the issue is actually not so dramatic, because we were mostly painting stellar mass onto the halos, and then we gave it thumbs up or thumbs down for our process enhancement, as kind of just it's there or it's not, and then just follow these systems to kind of see where they go statistically, and to see, is the Milky Way collecting enough of these, thumbs up systems to get us what we need. And so this was more of an exercise than really tracing our process and chemical enrichment.
Okay. Fair enough. Thank you. Case? No? Yes?
Yeah, I have maybe a bit a naive question. So you were talking about these very low metallicity stars that may have just one enrichment, event essentially before them, and you were also talking about these neutron star mergers being extremely rare. So my question is, in these dwarf galaxies, in the total dwarf galaxy, how many neutron star mergers have happened? Are we talking about of the order of one, or are we talking about of the order of hundreds? Or
rather one.
And so could that be then really the difference between the ones that have that have these R process enrichment and the ones don't, that is just a random, whether it's 1 or 0?
It seems like it. I mean, these 15 or so ultra-faint dwarf galaxies, there's no R process signature in any of them besides Reticulum, and then the jury is out on Tucana II. So it's yes or no, because either you have one, then you can't escape, or there's just nothing. Why that would be the case is part of how you make a binary neutron star, a pair to start with, right? Because that needs to survive the two supermassive explosions. So I can't tell you, but it's definitely 1 out of 10 or 1 out of 15, and if you kind of scale this up, the R process signatures in the classical dwarf galaxies, it was the reticulum-like systems that formed and to make classical dwarf galaxies, and the years were more diluted because more star formation, more gas was present, and so I think these guys are really rare, and in the small systems, the chance for you to have 2, I think, are very small.
I have another question, which is prompted by the fact that halfway through again you said that you couldn't really distinguish whether you were looking at a cluster or a dwarf galaxy. And the amusing thing about globular clusters is there exists this strong metallicity floor at about -2.5. Now one of the questions is, of course, okay, did these globular clusters with lower metallicities actually never form? Or did they form, and were they then disrupted of a cosmic history? So do you have a way, just by looking at the chemical abundances, to tell if some of these extremely metal-poor stars could have been in a globular cluster-like environment? Are there certain, I don't know, abundance variations that you could look at to try and make that distinction?
Well, I mean, they're the typical cluster chemical signatures, like the anticorrelations. We usually don't see that in any of the dwarf galaxy stars. Tucana II in particular has a metallicity that's consistent with the low metallicity clusters, namely -2.3 or 2.2. And there are, of course, always issues with the radial velocity dispersion, with the velocity dispersion, and the unaccounted for binarity of some stars that can, puff up things. I think that's the particular problem there. I have no idea about super low metallicity clusters and why they are not there. They are just a total mystery to me. Because any and all of these early structures, they seem to only be able to produce few stars.
Yeah.
And this is
maybe that's
clusters
yeah.
where you have 1 million stars. It's just totally different. I have no idea.
More questions? Yeah, Catherine.
So the stars that you find very far out radially in the very low metallicity stars. So how you're finding them photometrically? So how do you rule out that they're not Milky Way halo stars that are also low?
Oh, so that was in one of the. So we confirm the radial velocity. So they are then once we have a spectrum, we look at the radial velocity, and actually we did. Observe more stars than I even showed, and they were ruled out by means of the radial velocity. So there is really no other star there that we could have missed. Anything that we saw in the data and that remotely looked like anything, we did observe, and yeah, a whole bunch got thrown out. So we're left with spatially coherent, well, proper motion coherent, low metallicity, radial velocity corrected sample that's pretty tight. It's okay.
At the beginning of your talk, you mentioned that you wanted to say something about the dark matter content of this ultra-faint dwarfs. Was it related to the large extension, or was there even more to it?
Well, so yes and no. It was about that we are mapping the profile now with stars that actually extend past the half-light radius. Significantly. That the profile outside the half-light radius so far has always been guessed. Always, because there has been no data. So we now have data, right? We are currently quibbling with the fact how this will change, for example, the indirect searches for dark matter detections, because we have a different profile, and we have smaller. That means we have smaller uncertainties in the mass, and we weren't quite sure how much of an increase in the mass that yields. So far, it's a factor of 2, but our radial velocity uncertainties are also, we like them to be 1 or 2 kilometers per second, and the MAGE numbers are like 4 or 5 kilometers per second. And so we are currently exploring how the profile and how the mass depends on just that. And so if we were to get even better velocities, how that goes. And again, the big implication here is that we have this kind of sparse evidence from the other systems that probably all systems That's my best guess right now. Or a large fraction of the system have this extended halo. So we may need to model and revisit the masses of all of that entire population of ultra-faint dwarfs, and it will just change the numbers a little bit. And in the best case, the numbers actually don't get changed a lot, but the uncertainties will be decreased by a factor of a few.
Okay, thanks.
Then I have a final question. So it seems that statistics is really the big challenge here, right? You find small numbers of stars per galaxy, and I find it absolutely amazing and impressive how much you're managing to extract out of those few stars. You're showing the GMT here. With facilities like that, is there a chance that you could actually start to do a similar small number game in, say, the halo of M31?
That's the ultimate goal. Yes, that's a picture of the GMT. I hope it'll emerge eventually. It's not going to be 2022, actually, I'm just seeing. More like 32. But we'll get a few magnitudes from this one. Again, if you put a narrowband filter on that telescope and it's well characterized and we've really done the homework, what we're doing now, to understand, can we improve our filters so with the carbon-rich stars don't show up there? Can we cut them out? How can we characterize this? How can we use Gaia data out to whatever magnitude? I mean, we will need Gaia data out to very faint stuff. The answer is hopefully yes, but yeah, we have a little bit more work to do in the meantime.
And we have to wait. Yeah. Yeah. Okay, good. Before we thank Anna again, I can't see because of the projector. Okay. Before we thank Anna again, first we're going to go for the colloquium dinner today at Alge. It's a restaurant just behind the train station seen from here. If you would like to join, please contact Norbert immediately after the colloquium. The PhD drinks that we had last semester are integrated into this, so we'll start with some drinks and then eventually transition into dinner. And then next week we will have a colloquium by João Alves from the University of Vienna. Refuses to do that. Let's try this again. There, okay. Who is going to be talking about all kinds of other exciting things that you can do with Gaia data, and specifically we'll talk about the structure of molecular clouds, stars, and so on in the direct environment of the Sun in a talk titled The Rise of the Milky Way. So that is next week. For now, let us thank Anna again for a wonderful talk.